In our next section, we're going to look at the basic operations of BGP and specifically talk about how BGP autonomous system numbers work, and then also talk about how we establish BGP peerings. This is actually a very complex policy, or a very complex situation in BGP of how the BGP peers are actually established. It's not as straightforward as in IGP, where you simply turn the process on the link level, the routers automatically find each other, and then establish the adjacency. In the case of BGP, there are a lot of things that we need to take into account before we turn on the peerings, because ultimately the peerings will dictate how the traffic is forwarded, depending on whether we're dealing with iBGP versus eBGP peerings. Now, first off, we need to talk a little bit about the BGP autonomous system numbers, which basically are the numbers that we use in order to source the routing updates from, where the official definition per the RFC is basically a router's under a single administration. But there are cases where companies might have more than one BGP AS. So you may see that if one company merges with another, maybe they have multiple autonomous systems, and instead of merging the networks together, they'll just maintain both of them and then internally run eBGP to each other in order for policy separation. So the AS doesn't always necessarily mean it's a separate network. It mainly just means that it's a separate routing policy. Now, the ASs, specifically the autonomous system numbers, are allocated by IANA, or the Internet Assigned Numbers Authority. And if you go to iana.org under numbers, this is where you would actually apply to get an AS number, and then you go to whatever your local registry. So for example, if you're in Asia Pacific region, you would go to APNIC. If you're in the US or North America, you would go to ARIN. And then these are the ones that actually own the ASs, own the address space, and then they're in charge of the allocations. So as you go down here, like under IPv4, this talks about not only how do you get addresses for provider independent space, but then it also talks about autonomous system numbers, how do you register for one. And if you click through this, you'll see basically there's a bunch of requirements that they have you go through before you actually get an AS assignment. So it's not as simple as just send them an email and say, give me an AS number. Now, the actual AS number values were originally a 2-byte field. So the values were originally 0 to 65535, which is a 2-byte values to the 2 to the 16 possible numbers. And the last 1024, I believe it is, maybe 1023, are the private AS numbers, which were not able for allocation. So there were about 64,000 and change that were available for the public ASs. But the issue was that as the network starts to grow, they start to run out of BGP ASs. So fairly recently, they upgraded this to a 4-byte field that is the BGP 4-byte ASN. It is supported in our code as of 12.4.24. It was supported, and you can see the RFC there specifically is 4893 that talks about the BGP support for the 4-octet AS number space, or basically the 4-byte AS. Now, the reason that this is significant to talk about, though, is that when you're dealing with the 4-byte ASs, we need to make sure that we are maintaining backwards compatibility with routers that only have the 2-byte space. So when they go to receive an update, if the BGP update doesn't understand what the actual value is of the 4-byte field, simply because there's no room to encode it, then they would not be able to accept the update. And there were actually some problems on the internet when this was first implemented, that the 4-byte ASs, there's a backwards compatibility, and the issue is that it overran the buffer of the AS space, and all sorts of internet routers started to crash in the core of the network. So in most cases now, it's not really an issue, because as long as you're running a relatively new code, you should be able to support this. But there is backwards compatibility by encoding the 4-byte AS into an AS dot notation as AS23456. So we'll see this a little bit later as we actually do the interoperability between the versions and look at the 2-byte format versus the 4-byte format. There has to be basically this special encoding, and then there is a new optional transitive attribute that is called the AS4 aggregator and the AS4 path that is going to basically tunnel the autonomous system path and the actual AS value, who did the origination, through the device that doesn't support it. So we'll see that when we start the BGP process, this is specifically the first thing that we need to decide is whether we're going to use a 2-byte AS space or whether we're going to use a 4-byte space. So you say router BGP 1, that means your AS is 1. If you say router BGP 1.1, then that's a 4-byte value. Now, once we turn the BGP AS on, so we get the assignment from ARIN or APNIC, whoever is actually doing the allocation, then we're going to establish the BGP peerings. Now, again, if you don't want to use BGP for global internet routing, these numbers are arbitrary. You could pick whatever you want as long as your address space does not leak out onto the global internet. So they do still have a private range that's inside the 4-byte ASs, but you don't technically need to use this. We can use a BGP AS 1, 2, 3, 4, whatever we want, as long as we don't peer to the global internet. The issue we would run into then, we'll see when we talk about loop prevention with eBGP, that if I find my own AS number in someone else's route, I won't be able to accept that route in and use it because that's the native loop prevention mechanism. So once we have the AS configured, then we're going to establish the peerings. Now, like IGP, this is going to be our first step, that we need to figure out who are the other routers that we want to exchange information with. The main difference, though, is that BGP doesn't have its own transport. So what this means is that you don't enable BGP on the interface and then say, I want to route with the neighbors on that connected link. We need to specify who is the TCP destination that we want to establish a peering with, and this is assuming that we already have underlying transport. And this is one of the reasons, again, that BGP is not considered a routing protocol per se. BGP is an application to exchange reachability information. So the neighbors are not discovered by default, but the neighbors do not have to be directly connected. So this means as long as we have TCP transport, then we should be able to peer to whatever router. So if you have, let's say you configure a router in Amazon Cloud or whatever cloud provider you have, and you want to do an eBGP peering to them, basically as long as you can ping the router, because that means you have transport to them, you should be able to establish the session. Now, we'll see that there are disadvantages of doing this, though, because BGP then does not understand the underlying topology. So if I do a multi-hop eBGP peer or even a multi-hop iBGP peer to some router, when I actually go to route the traffic, BGP is going to have to pass that information down to the IGP in order to actually do the route recursion and actually do the traffic forwarding. So again, very key point here that the BGP process is just used to exchange the application information, where in our case the application information is the route. It's up to some other protocol in order to get the traffic actually there. Now, specifically, BGP uses TCP port 179 for transport, and it's a unicast source, unicast destination, which again means that we need to have transport to begin with. Now, in the case of eBGP peering, so you peer with your ISP, normally you're already directly connected to them. So they give you a Metro Ethernet circuit, they give you a legacy frame relay DS3, and you can ping the other side of the link. So you go into the BGP process, configure the neighbor statement, and that points to the directly connected link. You already have transport because it's directly connected. But in the case that the neighbors are not directly connected, then it means we need to run IGP in order to get there. Now, what the neighbor statement actually does under the process is essentially tell the process to bind a socket. So it's similar to when you turn Apache on for your web server, that it starts listening at port 80 for any connection to come in. Then you can configure rules under the Apache process to say, I don't want to accept connections from the address 1234 or 5678. Now, in the case of BGP, it is strict as in what neighbors will come in order to match against the socket. So what this specifically means is that if I issue the neighbor 1234 statement, it means that not only will I initiate a session to the destination 1234, but I will listen for a connection inbound from them. Now, the reason that this is important to understand is that the client and the server have to agree on this address. So if the server that is listening at destination 179 hears the TCP SYN come in for the first portion of the three-way handshake, and it doesn't match the address that it has configured locally, it's not going to accept the session. So we can see this on the CLI if we look at the show control plane host open ports. This tells you what addresses is the router listening on and what ports does it have open. So for example, if the router is an NTP server, we would see UDP 123. Or if it's running BGP, we should see TCP 179, but the socket should only be bound for that unicast neighbor that we're specifying under the process. So this means that we have to make sure we know where is the packet coming from to begin with. Because when we look at the routing table and we determine how am I actually going to send a packet to this destination, when the router generates the local control plane packet, it comes from the outgoing interface in the routing table. So let's think of this from the topology point of view. Let's say that we wanted to establish an eBGP peering between router 4 and router 5. And let's assume that we're trying to do this peering on this directly connected link here, which is gig1.45. So we go to router 4 and we configure a neighbor statement that points at that address. And we go to router 5 and we do the same thing. We point a neighbor statement that goes out that address, points to that address. Now, when the routers decide how am I actually going to send the packet in order to get to this destination, it's going to look at the local routing table. It says, what's the longest match to router 4's address? In this case, it turns out to be my connected link. So then I look at what is the source address that I have configured on the link. What's the primary IP? That address becomes the source of the packet, and then I generate it and actually route it out the interface. Now, what the potential problem we could run into, though, is let's assume that router 4 peers with router 5 on this link, but 5 peers to 4 on this link. They will not be able to establish a BGP peering. So we'll see that there are cases where if there are multiple links for transport between the devices, typically the easy way to solve this is simply to use a loopback. So we source the packet from the loopback, destine the packet to the loopback, then regardless of what the underlying transport is for the TCP session, we should agree from the client and the server when we do the handshake, what's the source and what's the destination. But we see that this is a significant value because if I were to point the neighbor statement at that interface and the interface goes down, it means the socket is no longer bound and the BGP process is going to go down. Now, beyond the regular establishment of the peerings, there's two different types of peerings that we need to talk about. The difference between external peers and internal peers. Where eBGP neighbors or external BGP peers are devices in different autonomous systems, and internal peers, iBGP, are devices within the same autonomous system. Now, the difference other than the peering establishment rules, there's going to be a big difference of the loop prevention, how the routes are advertised, and how the attributes are actually generated inside of the updates, inside of the NLRI. So we'll talk about this in much more detail later. How do they actually differ in things like next hop processing versus advertisement rules versus loop prevention? But as from a general transport point of view, one of the big things to think about is that there is a different time to live value when the router actually generates the TCP packet. In the case of an iBGP peering, the TCP packet is generated with a TTL of 255. For an eBGP packet, it has a TTL of 1. So this means under normal circumstances, the eBGP peers would be directly connected. The iBGP peers can be wherever we want as long as we have transport between them. So again, we're going to come back to this in much more detail later, but this is going to be a key point when we just look at configuring the peers. So let's go ahead and look at this on the CLI, where we're just going to start a basic BGP peering between router 4 and router 5. And for simplicity, let's say that router 4 is going to be in AS4 and router 5 is going to be in AS5. Now, before we do this, we need to make sure that we have transport between the devices. So let's go to router 4 and let's just look at the show IP route. And this directly connected link, which is gig1.45, is what we're going to use for the peering. So we need to make sure that we can ping 155.145.5, which we can. Transport's there, means that BGP should be able to establish. Okay, next let's go ahead and do a packet capture. So let's say that on the interface gig1, I have my IP address that's going to connect to my VM that's running Wireshark. And the VM is 10.0.0.100. Okay, I can reach the server. And make sure the server is running TFTP. And let's go ahead and create our capture. So on router 4, we're going to say monitor capture 1. We're just going to match anything. And the interface is going to be gig1.45 in both directions. Monitor capture 1 start. Okay, so next let's go ahead and turn the BGP process on. So router 4 globally is going to say router BGP, and then we can see we have two different formats. We can either use just the decimal value, either in 2 bytes or 4 bytes, or we can use it in the AS dot notation. So again, this is like an IP address using the dotted decimal format. When you look at it in the packet is always binary. So the router doesn't care how you notate it as the dot or whether just the decimal value. The decimal there is for us visually, that it's more difficult to remember that your AS number is 429496 whatever versus 100.200. But from a packet point of view, there's no difference between using the decimal value and using the dotted decimal value, or the AS dot. So let's say here that router BGP, our AS is 0.4. Actually, I can't start with 0. Let's say 4.4. Okay, 4.4, and I'm going to configure a neighbor statement. The neighbor is 155.145.4, 5, and their AS is 5.5. Now, before we configure anything else on the other side, let's look at what router 4 did locally in the control plane process. Okay, first if we look at now the show control plane, or show, what is the show command I want? I want to see show control plane, host open ports. Maybe it's not on this version, let's see. Let me type the whole command in. It may be, actually, let me look up in the documentation here. Under 15.3, actually I need to go to the master index. Let's say master index for show commands. Show would actually be previous one. Let's say control dash plane, show control plane host open ports. Why does it not allow that? Maybe the, and it says it's inexact. Let me just try to paste it in. Maybe the control plane process needs to be on first, control plane. Control plane host. I'll have to double check that this show command is supposed to be here. I'm not 100% sure why it's not taking this. But let's look at the capture instead. Okay, so at router 4, if we look at the show monitor capture 1 buffer, we do have packets. So let's go ahead and export them. Let's say monitor capture 1 export to TFTP 10.0.0.100, and we'll say router4.bgp.pcap. Okay, so let's look at the capture of this, router4.bgp, and we see that it's trying to send all this TCP traffic. So let's look at the very first one, which is the TCP packet coming from router 4, and let's look at specifically what's happening inside of the frame. So it says, first off, we have IPv4, and the payload is TCP, so the protocol is number 6. The source is router 4's unicast address, and the destination is router 5's address that we issued the neighbor statement for. Again, the reason router 4 picked this source address is it looked at the routing table. It says, how do I route to get to 155.145.5? It points to gig 1.45. The IP address configured on it is the 45.4, so that's the source of the packet. Again, we'll see that this is an issue to think about because if you route out the wrong link and you don't change the update source, then BGP won't establish. Okay, next we have inside of the payload. So we have the basic IP header. Now we have the TCP header. TCP says that this is a SYN. So of the three-way handshake, we have the client that's talking to the server. The client is supposed to send the SYN, which is step number 1. Step number 2 is that the server is going to reply back with SYN-ACK, saying, I acknowledge that you're trying to open a session, and I agree with this. And then lastly, we have the acknowledgement from the client back to the server, and then we can actually send the data. Now, in this case, we can see that the SYN was sent on destination port 179, which it decodes as BGP. But if we look at the next packet beyond this, router 5 received it, and it says ACK reset. Or in other words, I do not currently run the BGP process with your address. Now, this is self-explanatory in this case why router 5 is doing this, because I didn't configure it with the BGP process. But we would see this also would be true if we did configure BGP on router 5, but we configured it to the wrong neighbor address. It's going to reply back with the reset. So from a real design point of view, you actually may want to filter this out so that these packets don't hit the control plane, because it actually is a security issue, and you could basically do a denial of service against the router by pounding it with these random TCP frames in order to get it to send the resets back. So if we just filtered it out with an ACL, then it would never even get up to the CPU. But assuming that we want to run the process, the next step is that we need to go to router 5 and configure it to accept the session. Okay, so let's go to the other side, and let me make sure that, let me try this on the other routers to see, maybe this is a problem local on 4. Maybe this platform just doesn't support that command. It normally is there. I'll have to double check that later. But next, let's go to router 5, and let's configure the neighbor statement as well. So on 4, if we say show run section BGP, we have the BGP process, and notice here it shows you in the decimal notation, but I configured it as 4.4. So from a visual point of view, it's easier for us to understand it as 4.4 as opposed to, in this case, 264.148. It's just going to be easier to remember when we go to type the commands in. There is a command to change the view here. I'm not 100% sure offhand exactly what it is. Let's say BGP. I'll have to double check that. Maybe it's under the process. BGP 4.4, BGP. It's like AS dot notation or something. I'll take a look at that when we're on our next break. But on the other side, if we go to router 5, let's say router BGP 5.5, and we're going to peer with 155.145.4, and the remote AS is 4.4. Okay, we should see that the peer comes up if we look at the show IP BGP summary. This is our main verification of the basic transport. So did the router actually establish the peering? And if so, what are the other attributes of the neighbors? So from this output here, the most important thing that we're really looking at is, did this peering establish, and am I receiving prefixes from them? So right now the state is not down, and we're receiving 0 prefixes. This means that everything is okay. Now, we're not actually routing anything yet because I didn't issue any network statements. But at least this tells us that the basic peering is up. And somebody said that it is default, under the BGP process it is default BGP AS notation dot. There. Show run section BGP, now it shows it. No, it's not there. Why is it not showing that? This I'll check later. But anyways, we can see that the peering is up. Let's go ahead and look at in the packet capture exactly what happened here. Or here. Oh, it's just BGP AS notation dot. BGP AS notation dot. There we go. So you may want to put this on because otherwise, and we'll see like in communities do the same thing, that they use the decimal format just from the show run output. But again, in binary in the packet, it doesn't matter. The router doesn't care if it's 4.4 or if it's whatever the string is, because when it actually encapsulates the frame, it's the same value in binary. It's just from our point of view, it's easier to say this, 4.4, than it is to say 262.148. Okay, but let's look at now what changed in the control plane between them. So let's go to the capture. And you can see these red ones. These are basically, they keep trying to do the handshake over and over and over. It keeps getting reset. And then eventually we should get down to the portion where now we get to the BGP open message. Okay, this specifically is starting here at frame number 85. 85 to 87, this is the three-way handshake. Okay, in this case, the three-way handshake originated from router 5. And if we look in the details here, it should show us that the packet was a SYN. The packet was a SYN with a destination port of 179. Destination port 179. It came from router 5 going to router 4. And it says, I want to start the BGP process with you. Now, inside of this, we don't yet have all of the details of the actual BGP peering. The only thing they're doing is saying, do you have a socket bound on 179? Can we start the process? Once we establish transport, then BGP is going to run its application data. But normally what we should see here is that if the routers agree that they even have a peering for each other, and I'm not sure if you guys can see it exactly there because it's a little bit small, but we have the SYN, the ACK-SYN, and then the ACK. So this is the actual three-way handshake, this one, and this one, between the three of them. So once they agree upon that, now they go to the open message. Okay, open message is now where we're going to start to actually exchange the BGP information. So we can see this is where they go through what we call the capabilities exchange. Now, the capabilities exchange, we're going to go through in more detail later when we talk about what are the different multi-protocol extensions. But the one that we really care about here most is AFI1 SAFI1, or in other words, IPv4 unicast. What this is basically saying is that the routers agree that we're going to run normal global BGP routing. So whatever routes you have in show IP route, those are the ones that would be subject to the BGP process. Now, again, we will see that BGP is extensible and it does run other applications. It's just that by default, the router is assuming you're going to use BGP for internet routing. If you want to use it for MPLS, you can, but you have to turn that on. It doesn't happen automatically. Now, in addition to this, there's other capabilities that they're advertising to each other. One of them is the route refresh. One of them is support for the 4-octet AS number capability, where basically the routers have to agree that, okay, I want to run 4-byte AS, but you don't. That means I know that I have to run compatibility with you. So someone had asked the question, what if they don't run the compatibility? They automatically detect it. And they detect it through this capabilities exchange that goes through in the open message. Now, ultimately, once the peering is established, we should be able to see all of these details when we look at the show IP BGP neighbors. So in show IP BGP neighbors, and you'll see this is a very long output here, and we're going to talk about just what is the significant things that you might want to look at. Okay, one of them, of course, is that the BGP peer is established. So if the peer is not established, this means transport is down and you can't actually run any routing with them. So assuming that the peer is up, the next thing that we care about is what are the timers that we're actually using for them. So the hold timer is 180, the keep alive is 60. That's going to be the default value. Now, of course, you can change this, but one of the interesting things about BGP is that this is a negotiated value. So it's not like OSPF where if the hello interval mismatches, they won't form an adjacency. In the case of BGP, whoever just configures the lower timer is going to be the one that says we're going to use this particular value. So for example, if we were to go to router 4's process, router BGP 4.4 and just say BGP timers, where is it, timers BGP. Let's say keep alive is 5 and the hold time is 15. And then we clear IP BGP star, that's going to reset the process. When we now look at the show IP BGP neighbors, they've now renegotiated the capabilities exchange. And now they're saying that the configured hold time is 15, the keep alive is 5, and this is the actual value that we're using for that peer. Now, if we look at this on router 5, this is going to be different, though. If we show IP BGP neighbor, it's going to say my configured hold time was, and it says it somewhere in here, I don't know exactly where it is, but it's going to say my configured hold time was 60 and my dead timer was 180, but the other guy wanted it to be lower, so that's the one that we actually negotiated down to. So again, the point of this being is that if you want to change these attributes, these are part of the capabilities exchange. And the capabilities exchange only happens once when you do the open message. So if we wanted to change the timers, what does it mean from an implementation point of view? Doing just this is not going to do it. We need to clear the TCP transport in order to get them to regenerate the open message and regenerate the capabilities exchange. Okay, also, if we look into the details here, this is where they say, what do I actually support for BGP? Okay, again, the main one that we really care about here is address family IPv4 unicast, that this is advertised and received. This just means that we can run normal global BGP routing. So if I go to router 5 and issue a network statement for its loopback, router 4 will accept that because we're agreeing on the AFI, SAFI, or basically what are the address families that we're going to be advertising into BGP. Some of the other ones that are important here, one of them is going to be the route refresh and then also the enhanced route refresh capabilities. This means that if you want to make a change in your BGP policy and you don't want to drop the TCP session, you can ask the other neighbor, hey, I changed my inbound policy. Can you send me some new updates so I can actually affect the policy? This is what we call a soft clear or a route refresh. Because the issue is that when you say clear IP BGP star, this is what's sometimes called a resume generating event, which if you do this in the core of the network, you're going to have a very bad day. Because it tells the router to drop all the peerings, which means it drops everything in the data plane. And again, the goal of BGP is to be as scalable and stable as possible. So if we were to look at one of these route servers, let's say like routeviews.org, and we look at some of their peers, show IP BGP summary, ideally these peers are going to be up for weeks or even longer. So in this case, actually the router must have reset just not too long ago. But let's look at it from another one. Let's say like command authorization failed. We'll look at this later. But again, the goal is that the peer, you want it to be up for as long as possible. Because if you clear it hard, which is clear IP BGP star or clear IP BGP neighbor, it sends a close message or basically a TCP reset, which drops the handshake and then they have, or drops the session, then they have to go through the handshake again. And that takes time to reconverge. So in general, once you are actually converged, you do not want to issue this command. You would say clear IP BGP star out or star in, or even more specifically for that particular neighbor, inbound or outbound. Because this is what route refresh is for. It's to ask the neighbor to reapply the policy without having to regenerate the TCP connection. So we can still forward in the data plane. Then once I'm done with my new path selection results, I can write those down into the fib, and then we can actually make those changes for actual forwarding. But the idea is, in the meantime, you don't want to drop traffic. Just apply the new policy, but apply it in a non-disruptive manner. So these three are non-disruptive. Clear IP BGP star, that is disruptive. Okay, we can also see some other important things like what is the show IP BGP neighbor. Okay, we can see what are the prefixes that we're sending or receiving. Address tracking is enabled. This is a very important one that we're going to talk about later. This has to do with fast convergence of BGP and a change that Cisco made in the code from older versions, what used to be the BGP scanner versus now the BGP next hop tracking, or the NHT feature. So this means that if the peer goes away, you should immediately withdraw its routes instead of waiting for 60 seconds to expire and then BGP scanner to walk the table again. But you can see here, basically, the show IP BGP neighbor is showing you all of these details that they negotiated through the session. Like, they automatically knew to do path MTU discovery. Because if we're going over maybe a VPN tunnel, and the VPN tunnel doesn't support a full MTU, then I want to know what should be the maximum segment size that the router should negotiate in the handshake. Normally, this is going to be 1460, where 1460 is going to be the payload size, plus an additional 20 bytes for TCP, plus an additional 20 bytes for IP. And we can see this when we look in the actual packet capture. This is what they should have negotiated in the handshake, that when 4 replies back with SYNAC, it says the MSS is 1460, which again is basically saying this is the maximum payload size because I need to account for the IP header and the TCP header, where the IP header is 20 bytes, and then the TCP header length is, in this case, it's 24 bytes. Normally, it's 20. I think the 4 bytes is talking about something in the payload as well. It's the options here, the options. Then the maximum segment size is 1460. So then when we actually have our IP packet of 20, the TCP header of 20, and then the actual data of 1460, the idea of this is that when I generate an update message, I want to cram as many network layer reachability information updates inside a single packet so that it's going to converge faster. So for example, if we enable jumbo MTU on the router's interface, set the MTU to 9000 or 9216, the BGP process should say the MSS is higher, which means that you would converge faster if you had a full table to exchange, simply because it would be less number of packets that you need to actually generate between them. Okay, so next let's look at a case where this does not occur correctly. So next, let's go back to the routers and let's turn an IGP on. So let's say we just go to all of them and we say router EIGRP1 network 0000. So we're just routing EIGRP everywhere. Okay, if we go to router 4 and now look at the show IP route for 151.1.1, we see we have a route to router 1's loopback. Okay, now I don't really care where it's reachable out. In this case, it's reachable out gig 1 100, it's reachable out gig 1 146. I just really care that I do have reachability to it. Because again, BGP doesn't know about the underlying topology, it's only just trying to achieve transport to the node, and then we can exchange the application data. So let's say that we want to do a peering now between router 1 and router 4. So let's look at this back in the diagram. Let's say that router 1 is going to be an iBGP peer now. So router 1 is also going to be an AS4.4. And we're going to do the peering between their loopback addresses. Now, additionally, router 4, we're already doing the capture, so I'm going to add the capture to match these other interfaces as well. And then let's clear the capture route. So let's say monitor, actually let's do the show IP interface brief, pipe exclude unassigned. And let's say monitor capture 1, match interface gig 1 45 in both directions, gig 1, no, monitor capture 1 interface. I need to say monitor capture 1 stop, gig 45 in both directions, gig 100 in both directions, and 146. Okay, so I'm capturing in basically all lengths. Then monitor capture 1 clear, that's going to delete the buffer, and then restart the capture. Okay, next I'm going to go to the process, router BGP 4.4, and say we have a neighbor 151.1.1, and the remote AS is 4.4. So they're an iBGP peer. Okay, next we go to the other side. We go to router 1, And we do the same thing. We say router BGP 4.4. The neighbor is 151.4.4, and the remote AS is 4.4. So we're trying to establish, again, a peering between the loopbacks of router 4 and router 1. Okay, this is an iBGP peering. They're in the same AS. Now, if we look at the result of the capture on router 4, but actually, first off, let's look at the show IPBGP neighbors, or actually show IPBGP summary. The neighbor is not up. Okay, this is a bad output. This means that not only is the peer not working, it means the peer was never working to begin with. So this is a different output than you would see if the peer was up originally and then went down for some reason. Then it's going to tell you. This is a clear indication that something is configured wrong from the get-go, from the start. So something is broken between the basic transport. But the thing is, if we do a ping and ping 150.111 from 151.4.4, we have the transport. That's not the issue. Okay, so let's look at in the capture, what did router 4 actually do? Let's say monitor capture 1 export to TFTP to 10.0.0.100 / R4 to R1 BGP.pcap. And let's look at the result of this. Okay, we should see, and let's get EIGRP out of the way. So let's say apply a filter, not selected. Let's say ICMP v6, IPv6, apply a filter and not selected. And we have a tunnel. Let's get rid of that. Let's say for ESP and not selected. Okay, we're left with just BGP and TCP. Okay, so somewhere in here, probably towards the bottom, we have a peer that is going, so that's when I did the ping right there. It should be a little bit above this, that we're trying to start a peering, and I'm looking for a TCP SYN, which is this. Okay, what this is specifically showing us is that router 4 tried to start a BGP peering with 1. It says the source was 169.254.100.4, which is actually the underlay interface for the DMVPN, but it doesn't matter. It's just any arbitrary link here. And we're trying to peer with 150.111. So we say we want to start the handshake. We're sending you a SYN. The maximum segment size is going to be 1460 because we have no other options. We're not using jumbo MTU. Destination port is 179. And then some of the other values, like what's the window size that we support. These options, you can't actually change them on the router. We'll talk about this a little bit later under like miscellaneous things. But you can, if you wanted to use jumbo frames, you could force the router to do that. But let's look at now what happens after this. And also, actually, another important one, which I did not show before, is if we look at the time to live value. There's a difference here in the time to live between the iBGP and the eBGP packet. So this one here is the eBGP. This one here is the iBGP packet. Now again, we can change this. It's not an issue. It's just that the default behavior is that for an external peer, the time to live is 1, which means if there are more than one hop away, you won't be able to form the peering. So you can say either eBGP multi-hop or you can say TTL security. We'll talk about that in the next section, but it is something that you need to take into account, that if they are more than one hop away and they are not in the same AS, the handshake won't work because the packet just gets discarded. It goes TTL expired. Okay, so let's look at then the next frame after this. So what frame number was this? This was 234. Then frame 235 should be, no, wait a minute, where was it? That was the old capture. Let me start this over. I lost where we were at. And I'm looking for, here's the pings. It should be right above the pings where it was router 4 sending the SYN, and then this one. Okay, if you look at what's actually going on here, we don't even need to open this up to see what the issue is. Router 4 sent to 1 the SYN saying, I want to do the handshake. It came from 4's address 169.254.100.4. It went to the loopback of 1. 1 is replying back to 4 with a reset. It says, I don't have a matching neighbor statement for your particular session. Now, I do have a neighbor statement that's pointing towards your loopback, but the issue is I don't know that you're the same router. Because again, BGP does not have visibility of the topology, so it doesn't know that router 4 has multiple addresses. So this means right off the bat, when you establish the peerings, it is significant what addresses that you choose. In general, we would see that for iBGP peers, they should use the loopbacks, because that means that we can reroute around a failure in the IGP. Because here, router 1 and router 4, they have multiple connections to each other. They have that connection on gig 1, 146. They also have the link over the DMVPN tunnel. They have the link on the underlay. If any of those goes down, we should still be able to maintain a route between the loopbacks, and then the BGP session is going to stay up. Now, we'll talk about that when we get into details of convergence in IGP versus BGP convergence, where we would not want BGP to immediately flap when IGP is going through a reconvergence event, because we want them to be able to maintain that table state while IGP is rerouting the traffic from this link that got broken to another one. And again, typically we do that just by setting the loopback as the peering address. So specifically the way we do this syntax-wise is to go under the BGP process and say the neighbor 150.111, we're going to source the packet, or the update source is my loopback. Now notice here that I'm going to do this just on one side, and it's going to work. The reason why is it depends on who is the TCP client and who is the TCP server. And in normal cases, both of them will be both. And I did have a slide about this. Let me go back to this. So the BGP neighbor statement tells the process to listen for the address via 179, to initiate a session via 179, and if there is a collision, then the router ID, which is higher, becomes the TCP client. So BGP is a normal TCP application, which means that you send the traffic to the destination well-known port, the server replies with the source well-known port, so source 179, and then the client is going to return a traffic back to destination 179. Now, in this case, both of them are trying to send SYNs. They're both trying to start the three-way handshake with each other, but the issue is one of them has configured the update source correctly, one of them has configured it incorrectly. This means in this particular design, router 4 will always be the client, because when it goes to generate the packet comes from the correct source going to the correct destination. This is the SYN. When router 1 generates the SYN, it's going to come from one of the physical links. So whether it's gig 1 146 or whether it's the DMVPN or whatever, the point being that it's not the loopback. So when router 4 receives that in, it says, I can't start a session with you, because whatever address you sent it from, it doesn't match with my peering, and I don't know if you're the same box or not. So you can see here, technically you don't have to set this on both sides, but from a real design point of view, it doesn't make any sense not to set it on both sides. So there's no real advantage of doing this only on one side of the link, unless for some very, very specific reason you are trying to force who is the TCP client. So if you want the client to be router 4, then you just don't set the update source on the other side. There are some other options, and we'll look at all of these details here in the syntax. But you could also go under the BGP process and say the neighbor is 150.111. And then there's other options, like you want to say that is it the transport options. And you'll see that there's so many options here under BGP. Connection mode is passive. This means that when I establish the session to router 1, I will listen, but I will not originate a SYN. So they have to start the handshake in order for it to work. Normally, the connection is active both ways. So if I were to do something like this, let's say like from a troubleshooting point of view, and we show run section BGP, and let's say clear IP BGP summary, or clear IP BGP star. So now we're updating our resume, but in the meantime, notice what happened. 5 came back, but 1 did not. Because router 4 is saying, I cannot initiate a session to 1. 1 can initiate a session to me, but 1 doesn't initiate it from the correct source. So if we look back in the data, the control plane capture, we would see the SYNs coming in from 1, but router 4 is going to reply back with reset. So in order to fix this, I would either need to remove the connection mode passive or go to the other side on router 1, which is the normal case, to do this. To say, when I go to router 4, set the update source to my loopback. Now, we'll also see later that there are a number of other implications of using the loopback for the update source. In the case of MPLS BGP, it is required that the loopback be the update source, and it is also required that the loopback be a /32 host route. Now, that we'll talk about in more detail later when we get to L3 VPN and talk about how BGP VPN version 4 works, but it has to do with binding in the CEF table the label that I'm forwarding to the destination. So again, as a general case, in the case of eBGP, normally the eBGP neighbors will just peer on their directly connected links. For iBGP neighbors, normally you would peer them based on the loopbacks, because then you can reroute based on your IGP. There are some minor corner case situations that you might have eBGP peers peering on their loopbacks. That would be when you have multiple links between the same providers for redundancy. So let's say that you can't get Gig E, Metro E in your particular area. The best that they can sell you is DS3 frame relay. Well, you can buy 2 DS3 circuits, 2 45 meg circuits, and then advertise the loopbacks to each other, like just with static routes, and then do one eBGP peering between the loopbacks. The end result would be that we do ECMP for the BGP routing. Because as we'll talk about in the next section, the update source, or basically the BGP next hop, is ultimately what controls how am I routing the traffic via IGP. So again, and I'm going to hammer this into you guys over and over and over, BGP is not a routing protocol. It is an application. So there are all sorts of other implications about this distinction that BGP cannot be used to route the network alone. And there's issues that we can run into that if you try to do that, it simply won't work. Okay, there was a comment here. Could I repeat, who is forced to be the client in the case that only one of them does the update source? Okay, so let's say we have the peer between router 1 and router 3. Okay, we're trying to peer from this loopback to this loopback. Neither of them use the update source command. So we're going to assume that they're routing on this directly connected link in order to reach each other. This means that when router 1 generates the packet, it's going to say that the source IP is 155.1.13.1. The destination is 150.1.3.3. The packet routes out, and this is the start of the three-way handshake. It's the SYN. Router 3 gets this inbound, and it says, what is my socket bound to? So what is the source address that I'm listening for in TCP? And I actually may be able to see this. I don't know why it's not taking that control plane command, but I should be able to say show TCP TCB brief, or just show TCP DCB. This should show what sockets it has bound, which is these two. Or maybe just show TCP brief. Yes. So this shows you what are the current sessions that are actually running. This shows you who was the client, who was the server. Because router 4 is using the destination address 179. Router 1 picked a random source. This means that, and actually I need to see it from the other side as well. It should be that the foreign host is 4, the foreign port is 179. This means router 1 is the client. So the local port, this was the random port that they negotiated. The well-known port is 179. This means that router 1 was the first person to send the SYN, and then router 4 replied. But in this type of case here, that if I don't have the update source configured on both sides, then neither of them are going to allow it. Okay, so now let's say I go to router 1 and I say that the update source is loopback 0. What this means is now when I source the packet, it comes from 150.111. This is what the neighbor statement that router 3 has configured. So it means that router 3 replies back with SYN-ACK saying, yes, I will do the three-way handshake with you, and the connection completes. The end result is that 1 is the client and 3 is the server. But then the issue is if you have some sort of transport issue, like maybe there's an ACL that blocks BGP in one direction, then you might not be able to actually establish the connection. So in general, if you were trying to classify BGP from a control plane point of view, like control plane policing or maybe some sort of ACL, what you would want to do is something like this, is to say IP access list extended R4 to R1 BGP, permit TCP host 150.111 host 150.144 equal to 179. Permit TCP host 150.111 equal to 179 host 150.144. That the point being, you need to account for both cases, because you normally don't know who is the client and the server. Normally what happens is they both collide together, they both go to do the handshake, then inside the open message they say, this is my router ID, one of the sessions then gets dropped. Because it wouldn't make sense for them to have two separate TCP sessions in order to exchange the same data. But the point being is that it happens automatically, that you don't normally need to worry about who's the client, who's the server. It's just that on the back end, TCP does account for this automatically for you. Okay, there's a question. If you peer with a provider and the neighbor comes up, do you automatically receive the full table? Normally, no. And the way that it works is it's actually a very complicated process, that you have to sign a legally binding document called the peering agreement with them that specifies exactly what the parameters of the peers are going to be. That I'm going to either send you the full table, I'm going to send you my local view, maybe my connected customers and nothing else, or I'm going to send you just a default. Normally the provider is not just going to peer with you on a whim. It's like change control that you have to go through. It's a very strict process. So then you decide, do I actually want the full view or not? But the issue is most of the time the provider doesn't want to maintain a special policy just for you. So we'll talk about a little bit later what are the ways that we can influence the provider so that they don't have to maintain some crazy filtering policy, but we can manage it on our end. There's a feature specifically for this. It's called BGP outbound route filtering, or BGP ORF. But normally by default, you don't get a full view. There is no default parameter. The parameter is that you have to agree with the provider what you're going to get. Because the issue is that if your edge router is, let's say, like a 2911, it's probably not going to be able to take the full view. So you might be able to install the routes, but when you go to forward, it's not going to be able to actually do it. The throughput is going to be so low because there's too many entries in the CEF table that it has to sort through in order to actually make the decision for forwarding. But we'll see that there are other cases that we can fix this by doing things like MPLS tunneling, for example. Okay, there was a question, was router 1 peering with the loopback of router 4? Yes, it was. So that was a key portion of the example, that they both already had to agree that they were using the loopbacks. The only difference is that on one side I had not issued the update source.